Okay, I just want to talk about a top-down geometric framework involving zeta space and the spectral line. So the guiding viewpoint is a geometric framework where this quite mysterious space, zeta space, is regarded as a fibration over this thing called a spectral line, which I'll get to in a moment. The spectral line we are going to construct from inverse systems, specifically two different inverse systems, and glue them along a nexus, common nexus. Um, as an example, the first geometrically non-trivial level, or level three, the level three seed, and this would correspond to the light side, which is denoted there as plus, is S3 equals this triple of objects, which I've gone through before, and I'm assuming some familiarity with in this presentation. So the big sort of hypothesis is that there exists a space Z called zeta space together with a projection Q maps zeta space to the spectral line. Um, and an overarching interpretation is that the spectral line sort of carries these geometric slash spectral objects. On the other hand, the fibers um, over these objects are um corresponding to uh, zeta space objects, which are meant to or hypothesized to tell you something about the spectral line, the elements in the spectral line. So a good way to summarize that is we have this geometric spectral object and we have a zeta theoretic fiber above it. So in the finite stages, we should think of the maps Qn, where n is finite, um, the map from, say, Zn to a n seed. Um, and the notation zeta n is not to be uh, confused with to mean that the n seed is an object inside Z of n. So we can look at a commutative diagram here, which is the local square over the spectral line. Um, we have this zeta of n uh, as a fibration over Sn. If we go horizontally over to the right, we can map zeta of n uh, by performing the inverse, by taking the inverse limit of uh, the finite levels to get the entire zeta space, and then we can project down with Q once we get both the zeta space and the spectral line. As completed objects, we can project down and have that more simpler map from Z to L. And right now, this depends on the category in which is to be determined mostly. There are some hints, but yes, it's mainly to be determined in terms of interpreting this categorically. Um, but for the moment, we get we can express this in a way that is faithful to the program. So the spectral line, the nexus and towers. So like I said, the spectral line is built from these towers meeting at a nexus point. We'll define S 0 to be this nexus point. The positive or light tower is the inverse limit of the n seeds where n is greater than 0. Similarly, the negative or dark tower is the inverse limit as where n is greater than 0. So, or sorry, less than 0. Um, and then they're to be glued along this star or this S0 point to be completed. So right now we have this light and this dark tower. Okay, so for n greater than 0, we have these finite seeds, and the plus n and minus n represent this light and dark dichotomy. Um, so yeah, so the seed is defined like so as this triple plus these sign conventions. And yeah, like so to go through a little bit about what the triple involves is n is the family of top-dimensional geometric sheets. Gamma is the seam, graph, or the intrinsic stratified gluing locus. Pi is the group. Pi n is the stratum preserving symmetry group, which will all of these will be obviously become more profinite type objects. So for pi of n, it'd become a sort of profinite group. Plus or minus records the light or dark orientation of the tower. Now we're going to complete the two halves. So the inverse limits of the two towers are like so, and we denote that to be L or light, the light tower or light geometry. And that's going to be L infinity, and D infinity is the corresponding dark inverse limit, or the inverse limit of the negative n seeds. Okay, so a point of the inverse limit in a very elementary set theoretic picture is a compatible sequence, x1 through x2, comma x3, dot dot dot, where xn is some element in Sn, and p n plus 1, comma n, taking in xn plus 1 is going to return us xn. So, okay, so the definition of the spectral line. The spectral line is defined by joining the two completed towers over the common nexus. So we get the boxed equation. The spectral line L equals the push out over the nexus onto dark D infinity and L infinity. And the word line is not intended to mean that the spectral line is literally a one-dimensional manifold. Rather, it is in fact much different than that. It's a spectral object assembled from some inverse limits of geometrically enriched towers. So do not confuse this as the name is kind of boils it down to something simpler, but it's not literally a line as in the manifold sense. The spectral line. Okay, so the nexus is inherited from the S0. The inverse limit should be viewed as a completed spectral geometry, not just a single very large finite seed. And here's a little bit more about the limit and push out. This first definition at the top, it does not automatically imply that this that L is isomorphic to the limit, the inverse limit of out in front of this quantity. So we have to take care with that. Uh, there is, yeah, in general, there's only a canonical comparison map, theta L. And whether this comparison map is an isomorphism, homeomorphism, or equivalence is a separate problem. Uh, this is one of those questions that crops up, and we can try to answer it, arising from the construction I presented here. So zeta space over the completed line, the corresponding zeta data are also expected to form these compatible towers. So we're going to construct it in a very similar way. The fiber space, or the total space. We're going to construct this and this kind of mirror it in the way that we constructed the spectral line as sort of this these geometrical objects. Then we take the inverse limit, um, and then we push out from the nexus um, to get the completion. So essentially, um, yeah. So one important point is that the nexus in zeta space lies as a fiber above the nexus on the spectral line, and a possible realization of the global zeta space is Z equals the push out over the zeta zero, uh, sort of like the analogous nexus for but in zeta space, and we're going to push out to the D and L respective towers, together with the projection back to the spectral line. So essentially, we have this this square. And this is a good diagram to keep in mind. And fibration is the guiding idea here, but it may be expressed in different ways going forward, such as topological fibration or an orbit space fibration, Grothendieck construction, or related construction. So the main thing to see here is that it just basically gives this diagram gives uh, a, a big picture of what's going on here. So the geometry belongs to the base. One important point is the geometry belongs to the base, while spectral transforms belong to the fibers. So, and going forward in this presentation, I'll try to get to this notion of that these SN objects on the spectral at finite levels of the spectral line sort of like respond to some signal coming from the zeta space up the total space or the fiber space upstairs, and there's some sort of dual or reciprocal mapping that allows you to, well, obviously there's the projection and the inverse projection to get sections in zeta space, but uh, it's not entirely clear at this point what that rigorously looks like and how to go from all this stuff on the spectral line upstairs to say a unique fiber or unique fiber in zeta space, and how to go back down and reconstruct the SN corresponding to that zeta of n upstairs. Um, so yeah, so basically we have the spectral geometry sitting on the base. We want a way to transform it into a zeta fiber upstairs. All right, so the spectral tower, the finite stages SN are called seeds. A seed packages these three kinds of information. Like I said, so that these correspond to like so geometric sheets would be the IN, gluing strata, gamma N, global symmetries, which correspond to pi N. So it organizes these distinct pieces of information, but we'll see that they work together quite well in a cohesive, complementary way. So what each part records. The family IN records these top-dimensional geometric pieces, such as, like, for example, in I3, so n equals 3, we're going to have these orbifold or cone manifold surfaces, and we're going to glue them together according to the equivalence relations that gamma prescribes. And we're going to attach those along lower dimensional strata. So the group pi n records the symmetries that survive the entire gluing process. So if we can somehow build this this seed, and then if we can build it in a way such that it has this global symmetry group, then that is considered good. Um, so the structure is very, very much more refined than either just a disjoint collection of orbifolds or a bare simplicial complex, and it's a good amount different than like an orbihedron. Um, and yeah, so it's a little bit of a specialized object. The three seed, the first geometrically non-trivial stage of the light tower is S3, the three seed. And this would correspond to the light geometry side, so L. And that we denote that as a plus there on the right in the four tuple. The cubical scaffold underlying the three seed is an abstract three cube, and we know a three cube has four antipodal pairs of vertices. So these four antipodal pairs are our index set for the four geometric sheets of the three seed. So they act as a sort of scaffold to bind or attach these um, surfaces to, so the surfaces collapse, and that's where you get that sort of cone manifold structure. The four sheets. So I3 would be this collection of four cone sheets. Uh, we can additionally put a positive, a constant curvature metric, a positive constant curvature metric on these. But topologically, it's just S2, this two sphere. And each sheet has two distinguished cone points. So the four-sheeted geometry contains exactly 8 cone local ends. And this will be our basis for exploring the local theory of these seeds, these SNs. So the three seed is not just a disjoint union of these um, positive constant Gaussian curvature surfaces or cone manifolds. The four sheets are actually attached along or glued along this common intrinsic seam complex gamma 3. And you can think of you can picture Klein foams, dianalytic Klein foams, or seamed Riemann surfaces. There's a paper by Gusain Zaid, Natanzan, for Klein surfaces. And then there's I forget who the paper is for the seamed Riemann surfaces, but it's in string theory, like world sheets and such. The result is a stratified geometric object because we're gluing these cone manifolds slash orbifolds together. All right, so we can look at smooth geometric sheets, and like I said, we can put these, we can put positive constant Gaussian curvature metrics. In particular, it will endow these surfaces with action angle metrics, um, and like so, G sub G phi, where phi of u is the momentum profile, and phi is just quadratic. With A and B are, where A is two over square root of 3, and B is the equal to the Gaussian curvature here, and B turns out to be uniquely determined when we use this cubical scaffolding process. All right, so volume and curvature. The fundamental property of this metric, the determinant of G phi equals 1, the volume form du dv, the Gaussian curvature is constant, k equals b. So the regular part of each sheet is a smooth, positively curved Riemannian surface. The endpoints u equals 0 and u equals a over b are the two, correspond to the two cone points of the cone manifolds there. So the three seed combines a couple of things. Smooth Riemannian geometry, that is on the regular parts of the sheets, singular orbifold geometry at the cone points, and then this stratified gluing geometry along gamma 3. The seam complex gamma 3. So we can look at the seam complex. This is a very interesting part of this, is that it's this one-dimensional intrinsic locus where these four orbifold sheets come together and are assembled and glued. Combinatorially, gamma 3 is a connected four regular graph with 6 vertices, 12 edges. But actually, we're taking a very simplified view of this, because actually, when these four orbifold sheets are assembled with this cubical scaffold, they actually intersect in quite a complicated way. So we're when I say gamma 3, I mean just um, the outer a specific subset, outer subset of this whole intersection complex, one-dimensional intersection complex. And but it turns out that the gamma actually determines what's needed for the symmetry to exist in the global symmetry, and I'll try to explain what I mean by that going forward. Um, okay, so we're focused on this we're focused on this subset of the entire seam complex, but we'll color the distinguished cycles in this subset, gamma 3. So the seam structure can be decomposed into distinguished cycles, gamma R, G, B. These cycles are going to record the independent coordinate directions of the cubical structure. So gamma 3 carries incidence data, winding data, transport data, and symmetry data. Okay, so the symmetry group pi 3. The final component of the 3 seed is the finite group pi 3, and it sends. So okay, so for the symmetry group, um, we can allow it to be the global non-discontinuous group. So it basically maps the entire seed to itself, preserving strata. And it can say, it's just like turning, you can think of it like turning a block in 3 space. You look at a symmetry group there. So OH, O sub H, octahedral symmetry. Um, and yeah, so it's permuting the sheets. It's permuting gamma, but mapping all strata to strata. Um, and exactly the same strata to the same strata. So the action, yeah, like I said, the action is required to preserve the geometric structures carried by the sheets. So we're going to look at these GX structures on the sheets now. In the spherical case, we can just take X to be S2 and GX to be the symmetry group of S2, which is O3, isomorphic to O3. So the individual sheets, they're going to carry these GX structures, and when we have a seam E, which identifies part of E sub I, or sigma sub I, so when these seams overlap, basically let the germ as an element in this O3 denote the corresponding geometric transition germ. All right, so if pi, the element in the pi3 group, acts on the surface, this ith surface, by local geometric transformation, h sub pi comma I, element in GX, then we get a compatibility with the pi3 action with the seam geometry. To get a compatibility of the pi3 action with the seam geometry, we're going to require this equation here. So it says that the compatibility between the global symmetry group and the local GX, it gives us a compatibility condition between the global symmetry group and the local GX X geometry. So since these spherical isometries are real analytic, we also get an induced action on each sheet, which is dianalytic with respect to the conformal structure. So this means orientation preserving elements act holomorphically, and then these orientation reversing elements act anti-holomorphically. So pi3 can be viewed as a finite group of stratified dianalytic automorphisms of the assembled seed. And we can kind of visualize that by these orientation preserving elements um, as pi, if pi is essentially the octahedral group, this global group determining the symmetries of these seeds, or I guess hyperoctahedral group in general. But for pi3, we just have OH, the octahedral group. You think of putting these four orbifold sheets in orienting them. So maybe you choose a specific orientation, and if you flip the block completely upside down, then you may get, if the orientation is basically like pointing in the positive z direction or something, like if you choose it so that it's pointing in a certain direction and you flip it, reverse the orientation, you're going to get anti-holomorphic maps. So pi3 actually changes that, changes the holomorphicity. The three seed as a stratified geometric object. So the three seed is not a smooth overfold, and I alluded to this before, but it's not a simplicial orbihedron. Uh, it's individual sheets. How is originally constructed as disjoint, four disjoint orbifolds are genuinely smooth geometric orbifolds, but when you compile them and glue them, it ceases to have such a nice structure as an orbifold anymore. So cone local geometry to spectral data. So the next layer is spectral. The basic philosophy is cone local modes to global seam modes to Mellin data to Zeta objects. So the construction begins basically zoomed into cone points, so cone local stuff on the orbifold sheets. So we get 8 total of these, so we can look at 8 total of these. So each cone supports these angular or winding modes, And we can, if M in the integers denotes an angular mode, we can begin to build a heat or theta trace, which looks like so. Um, and this would be our cone local theta. Q is a quadratic spectral form, and it's determined by the local cone geometry, by the way. The exact normalization obviously depends on the cone angle and on the operator being studied. So let's look at dilation geometry. The multiplicative group of the real numbers, the positive reals, acts naturally on the radial scale of the cone geometry. So if we write the radial coordinate multiplicatively as u, the logarithmic coordinate r equals log u, it converts dilation into translation. And each cone local region thus carries a multiplicative transport structure. So you can imagine like these, you can imagine like S1s, just loops, S1s, like concentric S1s almost, but they're being fired out of each cone point, and they're basically like waves with no well, I guess like idealized uh circles that get shot out from the cone points. Maybe it's like an impulse gets impulse response system or something like that. But and then they kind of like collide at the seam locus. So for the 4 football sheets, one obtains 8 cone local dilation directions corresponding to 8 cone points. And these, like I said, these sweep spectral information from the cone local regions toward the seam structure. And the seam complex gamma 3 is the locus where the separate local transports become globally coupled. So then we do cone to gamma reciprocity. The central local to global mechanism is this ability to toggle between cone local and convert between cone local spectral modes and global winding modes on gamma. So at the theta function level, this becomes, you can write this down as the following. This is just bare from any seed interpretation so far. It's just the Jacobi reciprocity identity. Um, and it basically transforms T to 1 over T and exchanges small scale and large scale spectral information. All right, so in the current interpretation, one side of this reciprocity is attached to the cone local modes. Okay, and the dual side is interpreted through the winding or transport modes on the seam complex gamma. So schematically, we can write theta, the cone theta, and then it gets mapped to or converted to the gamma theta, where the map is achieved through this inversion of T. The cone points provide local spectral generators. The seam graph organizes their global compatibility. So now we do some pi averaging. The spectral data on gamma 3 ideally should respect the global symmetry of the seed. Right, so we want that. We want this. We want to be able to pass from a raw seam theta function to its symmetry group, shadow preserving symmetry group, invariant component. So we just take an average um, over the elements in pi 3. We kind of smear this theta across the whole seam graph. So this you lose some information, obviously, but it's one thing that we can do to retain, basically get a completed spectral object um, that isn't like I guess like a uh, vector valued thing. So the order of operations, we go from zoom in on cone local modes, use the go to cone to theta via reciprocity. And then we're going to go to global seam modes and then pi averaging. And after this, only after this global invariant spectral object has been produced do we apply the Mellin transform. Right? We want to sort of like put this in canonical form so we can or in nice enough form so that we can take the Mellin transform. It's not going to give us like an addition, like a sum of 8 different zeta functions. Okay, so we do that, take the Mellin transform, and we obviously subtract any constant or diversion terms required for regularization. And what we get is the Mellin transform converts the multiplicative scale parameter T into the complex spectral parameter S. And hence we can go through the classical argument here. So we get this gamma factor times zeta of S on the right there up top. So the chain of construction is basically the geometry to the theta, the spectral quantity over on the geometry, hit it with a Mellin transform, convert to zeta, zeta function. In particular here, in this case, this will be the Riemann zeta function. So next we'll look at the functional equation. So theta reciprocity provides the geometric origin of the involution S maps to 1 minus S. Okay, so the local transformation T maps to 1 over T becomes, after Mellin transformation, a reflection of the complex spectral parameter. So if we have the classical Riemann normalization, lambda of S, then we have that on the right there, lambda of S equals lambda of 1 minus S. And this is actually encoded quite well in the 3-seed because we can look at involutions of basically involutions from the seed to itself, which would be particularly there would be like basically involution. So you map the seed from different orientation to like its reverse orientation, and then squaring that gives it back to the identity. So actually, this pi group encodes very nice. There's some nice compatibility going on there with the S maps to 1 minus S, and then the seed symmetry global symmetry group. So the important distinction is between T maps to 1 over T. This is this local reciprocity between cone and seam spectral descriptions, and this global rigid S maps to 1 minus S. And that's what I was trying to explain in the slide prior, that we should maybe think of this S maps to 1 minus S as some sort of manifestation of this symmetry. That's the global symmetry, rigid global symmetry of the seed itself, mapping to itself. So the Riemann spectral object in zeta of 3. Beginning with S3, one extracts cone local spectral data, transports them to gamma 3, imposes pi 3 symmetry, and then applies the Mellin transform. We can look at this schematically in the following way. We start at S3, map to theta, cone theta, then with reciprocity map to gamma theta, then average the thetas on gamma, um, and then take the Mellin transform, where we get lambda of S. The Riemann zeta function is interpreted here not as the seed itself, but as a distinguished spectral object produced from the seed. All right, so schematically we can write this R is an element of zeta 3, where this R denotes the distinguished Riemann spectral object. And the 3 seed is not an element in zeta 3, but Rather, the 3 seed is the geometric source of the spectral construction. And on the other hand, R is its corresponding zeta space object. So the forward direction of the theory is that we move from the 3 seed to spectral signatures to zeta 3. Now, there is a deeper direction, which is the reverse. The hypothesis is that sufficiently rich zeta space data should be able to get us from that zeta space, and we should have a process to be able to recover the entire seed, including the spectral geometry from that process. So schematically, we start from upstairs, zeta 3, either descend via explicit formula or trace type construction. Um, so like some sort of trace over the spectral or over the non-trivial zeros, and maybe something like that too. And then we can recover this 3 seed, hopefully. And the inverse problem asks which spectral data in Zeta 3 are sufficient to reconstruct this triple which forms the seed, the 3 seed. And really we're asking about this for all the seeds, all the finite levels. But it's easiest to state um, for n equals 3 right now. So trace formula philosophy, the reconstruction mechanism is expected to have the character of a trace formula. So a spectral trace normally relates two descriptions of the same object, spectral eigenvalue data and geometric or dynamical data. Now for the 3 seed, the two sides are expected to involve zeros, or zero spectral parameters, Mellin data, and then cone mode, seam windings, and geometric transport. The 3 seed is the first non-trivial stage where this framework simultaneously contains um, low dimensional geometry um, in terms of smooth sheets, connected non-trivial seam complex, and it's not too complicated, not too high dimensional, non-trivial global symmetry, cone local spectral data, and non-trivial winding and reciprocity data. So this is the first non-trivial kind of like finite level you can kind of get your hands on and learn something about what's going on globally here. So the cubical data inside S3. So we have these distinguished seam cycles, gamma R, GB, and the four antipodal vertex pairs provide are these combinatorial scaffolds for the four overfold sheets. This is the first stage at which the seed acquires the full four sheet seam, symmetry, geometries, and zeta construction. Now, for the full tower, we expect a geometric object, Sn, just the nth dimensional generalization, together with these compatible bonding maps, and we also expect compatible spectral spaces as the fibers above, with their compatible maps. The assignment should commute with a projection to the geometric base, like so, and thus the global zeta space should remember not only the spectral data of one seed, but also their compatibility through the entire tower. And there's a possible categorical reading. If we associate a spectral object, if we associate to each spectral object S a space, then we can try to view the global zeta space as this total space of this following assignment. So Z is isomorphic or homomorphic or whatever. to this sort of Grothendieck fibration or Grothendieck integral, where the projection is going to send it and forget about all that and send it back to the spectral line. So the fiber over S would be Q inverse of S equals the fiber above that particular geometric location S. So at the 3-seed level, this becomes the input is the 3-seed, so S equals the 3-seed, and then you input that into the function, sends it up to the fiber, you get that point in zeta 3. So yeah, right now the categorical language is optional. And I want to avoid overcommitting too rashly to a particular category. Um, so here are some definitions versus hypotheses. Here are the definitions. And this is a developing program, so the following remain in development. And a brief full architecture diagram. And in summary, we have this chain, which is pretty fundamental to the full framework, is S3 to cone local geometry to theta to gamma 3 to pi 3 invariant spectral data, and then Mellin transform to get point in zeta 3. And the larger purpose of the spectral tower is to place this finite stage construction inside a compatible inverse system. So the final picture, the larger purpose of Zeta, and this is a very top-down picture here, which I implemented on purpose just to see, just to go from the most general sort of things that this framework predicts down to the most minutia or smaller details and constructions. So the resulting picture is not one geometric space goes to one zeta function, but rather spectral tower goes to the spectral line, and then zeta space fibration maps to the spectral line. So the 3-seed provides the first finite stage at which the full local to global geometric spectral mechanism becomes visible.